Okay, here we go. Good, good. One announcement first. Wednesday, we have no class. I have a trip back to Lake Charles. They have to ask us to move all the stuff from our office into some storage place. They're gonna have some mitigation process or whatever. So my time is in the afternoon, but I have to drive 5 hours back, so I have no time. And I think it's not possible to have the class on Wednesday. Okay, so if I had time, I can record something, but if not, let's just meet on Friday. Okay. Okay, next meeting will be on Friday. Okay, let me share my screen. Let's continue on chapter 2. Okay, chapter 2 has some good stuff, right? It's really helpful, you know, with the thermal resistance for us to solve heat transfer problems, make our life a little bit easier. Okay, let me share my screen. Okay, you can see it, right? Let me keep my waiting room open. I can admit people. Okay, this is where we are last time, right? We had an example here about you have 2 layers of conduction, okay? Then you have the convection outside the outer layer, and the overall thermal resistance is for this serial arrangement, the overall resistance just equals the resistance of the 2 solid layer plus the resistance of the convection air. Okay, and remember the formula of the thermal resistance, right? Delta X, the thickness divided by what? Let's look at the previous slides. It's log, it's not delta X. Delta X is the XY coordinate. It will be log over log outside diameter over inside diameter. Okay, then divided by the area, right? Okay, and the K. Okay, so that's the thermal resistance. Okay, so after we find out the thermal resistance, after we find out the thermal resistance of each items, then we add them up to find the total thermal resistance of the whole thing. Then use the temperature difference divided by the overall thermal resistance. Okay, so that's the procedure. Be careful. If you use this thermal resistance idea, the delta T temperature in the numerator has to be inside temperature minus outside temperature, okay? Because we get rid of the negative sign for the, remember, for that conduction, right? So we have to switch the order. Okay. Today I'm going to introduce another idea for calculating this. So it's called overall heat transfer coefficient. Okay, heat transfer coefficient, did that sound familiar to you? It's in convection, right? It's convection. So in convection, HA, you know, Q, sometimes I use lowercase Q, sometimes I use a capital Q. It's okay, I think the heat transfer rate, okay. HA delta T, remember this is when we calculate the convection. We call this H is convection heat transfer coefficient, okay. convection heat transfer coefficient, right? So it seems like some engineers like this idea. HA delta T seems like easier to memorize, okay? And it doesn't require like a DT dx, something like that. So why not create something called overall heat transfer coefficient? So it's slightly different comparing to that thermal resistance idea. So now the whole thing become, okay, if we want to calculate the whole heat transfer using this, let's say U is the overall heat transfer coefficient, delta T overall. Okay, we like to adopt this form, HA delta T. It seems like it's nothing new in this lecture comparing to the previous ones, but it's just different ways to do it. Okay, it's by different, you know, by the preference of some different engineers. Okay, so people maybe like this form, UA delta H. So let's say we'll create a overall heat transfer coefficient for everything from the beginning to the end. Okay. Instead of using the previous idea, delta T over R, delta T over thermal resistance, right? So basically, comparing to, okay, you see the difference here. This is really by preference on different people. Okay, so when you do the thermal resistance, if you use this way, then the thermal resistance, all the areas are included in the thermal resistance. But if there are many items in the systems, so the area is kind of like all different. Okay, so sometimes doing the area is a little bit complicated. Okay, so it's related to the geometry, right? Okay, it might make a mistake. So some engineers like to using this total area. There's only one area in this calculation. Let's move the area out of the thermal resistance calculation. Okay, because now then the problem is you have many areas, right? Every items you actually have different areas. Okay, so basically this UA delta T is a simplified version. It says, okay, I have a characteristic area of the whole system, which belongs to the most dominant heat transfer items. Okay, so basically it's the largest heat transfer coefficient. That item, that area is our characteristic area. Okay, that portion, that material is our control material, because he dominates the whole heat transfer process. Okay, so we only use that area instead of using all the areas to calculate all the thermal resistance. Okay, it's actually not 100% accurate calculation. It's kind of like a simplified version, but make it a little bit easier. Basically, we identify the most dominant heat transfer material in the system and use that area as the characteristic area of the whole system. Okay, then you will see, hey, what is U equals? U just equals to U times A actually is just equals to 1 over, let's say put the summation here. How about that? Usually there's more than 1. Okay, so if you divide it by area, both sides of the equation, U equals to what? The R times area. Basically, you try to get rid of all the areas. Okay. So I think you can do this. You can just, for example, you have a system, let's draw an easy system. Let's say, hey, you have a convection here, H1, you have a K here, you have H2. Okay, so in that sense, if you move A to the right-hand side, actually R times A in the denominator, right? So basically, you try to the idea is try to get rid of the area in the U calculation. So U equal to what? Actually equals to 1 over 1 over H1, notice, supposed to be H1A, right? Now it's just 1 over H1. Then it's delta X over K plus 1 over H2. Okay, so this is the material, this is the heat transfer, okay. Heat transfer direction, let's say this is the heat transfer. You have air, you have material, and then you have air again, okay. So notice this, now in the denominator, you don't have an area. Okay, in the U calculation, in the denominator, you have the area. But it looks like it's still thermal resistance, right? These are 3 items here. Where does the area go? The area goes to the left-hand side, okay? So when you do the calculation, you multiply by an area next to U. That's why you have this equation now. Q equal to U A delta T. Okay, so they're not equivalent. Basically, you have 3 different areas. But in this case, area indeed is the same. For in this case, the cross-sectional area for the air in the left, for the material, okay, for the H2, air in the right side, they share the same area, right? So it's okay. Air, you can move it out. It becomes U. If you calculate the U like this, times in common area, then delta T. That's exactly the same as what you do, what you use thermal resistance in this equation. That's exactly identical. But if you have a cylindrical coordinate, cylinder, layer by layer, they have same different A's, right? Okay, they have different A's, but still, we're forced to use this U A delta T. You have only one area. So which area you use? You find that you use this again, okay? Use this formula. Then you use the most dominant controlled, most dominant heat transfer items in the system as the control material. Okay, so that area we use that for the calculation. So this is a different approach for the same problem, basically. Okay, different approach. Okay, I think it's best way to learn this is let's look at an example. How about that? Look at an example. Okay, I think I like this example. It actually explained the process and explained the difference. Okay, so let's look at example 2.5. 2.5 on page 39. Okay, maybe I want to start a new page. Move the page a little bit bigger. Okay, here. Okay, here we go. Okay, example 2.5. Okay, so it says water flows at 50 degrees Celsius inside a 2.5 centimeter diameter inside diameter tube. Okay, so well, basically you have a heat transfer. This is convection H. Okay, inside this is the tube. Okay, flow in there. Okay, the convection inside. This is the tube, right? Okay. Inside diameter, 2.5 centimeter, okay. Convection heat transfer coefficient HI equals 3,500 watt per meter square C, okay. The tube has a wall thickness 0.8. The wall thickness, how to say, delta R, the thickness, right? Equals 8 millimeter, 0.8 millimeter, okay. Very thin. Okay, the thermal conductivity, K of this pipe, tube, let's say, is what, 16. watt per meter C. Okay. The outside diameter of the tube, loses heat by free convection. Okay, you have a convection HO outside. And the HO equals 7.6 watt meter squared C. Okay. Calculate the overall heat transfer coefficient, and the heat loss per unit length to the surrounding. Okay, heat loss. Well, we can do the heat loss first. Okay, we can even try that thermal resistance. Then we find out what is the overall heat transfer coefficient. Overall heat transfer coefficient is U, right? Okay. So you have 3 items here, obviously. Right? This is inside the convection. K, outside the convection. Okay. Temperature inside is 50 degrees Celsius. What is the temperature outside? To the surrounding air, okay. T out is 20 degrees C. T in, right? T in, HI, K, this is the conduction. Then the H out, HO, then TO, right? 50 to 20. So we know we have to find out the thermal resistance, right? Of the whole thing, right? So RTHI, let's just say RI, how about that? Okay, this is not R number, this is the thermal resistance, okay? Just want to make sure, okay? How do you calculate the thermal resistance? H over what? Or 1 over H I A I. Is that right? Everybody follow me? Any question? Hey, if you have any question, just jump in, okay? I don't care who asks question and what kind of question, any question. If you're not sure, please jump in, okay? We clear it out in the class. It's more efficient for learning, okay? So anyway, either way, you can use the thermal resistance to calculate the heat loss, right? Or you can use the what we talk about today, the U, to calculate heat loss. But either way, you have to find out the thermal resistance of the items, okay? So 1 over 3,500. How do you calculate the internal area?
Inside diameter times pi.
Inside diameter times pi, okay? So how about the length? I think it says unit length. Unit length, let's say L equals to 1. How about that? 1 meter. So it will be pi d times 1. I think that's what the book says, right? Okay. Pi d. What is diameter? Inside diameter is given, right? 2.5 centimeter. 0.025 meter times 1. Okay, so I think you can key in the calculator. It's 0.00364. Okay, degree C per watt. Look at the unit because it's 1 over, right? So it's the temperature per watt for the thermal resistance. Okay, so that's easy, right? The second one is a little bit more complicated, right? It's conduction, so you have to log over log. So it will be log dO divided by di over 2 pi K L, right? L is 1, so just 2 pi K. So be careful on the inner outer diameter calculation, right? Last time I made a mistake, right? So it's log outer diameter minus divided by inner. What is outer diameter? Okay, so inner diameter is 2.5 centimeter, right?
0.8 millimeter?
Yeah, so the diameter, 2.5 plus 8 millimeter times 2, both sides has 8 millimeter. So it will be 2.66 centimeter, right? 0.0266 over 0.025. Okay, so that's so 2 times pi times k. K is what, 16, right? It's given. L is just 1, so it's very tiny, 0.00062. Okay. So I guess, you know, just going through this lecture like this, I'm showing you to calculate the R's, okay? You should be able to 100%, all of you, 100% know how to calculate the R's, right? Okay. Not much, you know, difficult part here. Just follow the equations, okay? And carefully calculate the diameters, okay? Outside convection is easy. It's just 1 over HO times AO, right? 1 over, I think it's given. Outside the H is what? Very small, 7.6. Okay. Times area outside, outlet. Oh no, not outlet. Outside surface area. Okay. So pi D is 0.0266 as we discussed last, right? In RK, right? Times 1. Okay. So the value is much bigger. The resistance on the convection and at the outside is 1.575.
Why are you timing by 1 again?
Oh, it's a unit length. Unit length, you don't need to worry about unit length. Basically, you can just specify unit length in the SI system, which is 1 meter. Okay. Or you can calculate the Q divided by L. That's called unit length, heat transfer per unit length, right? So you move your L to the left-hand side, just as if it's not there. Okay. So either way, but you mark it. If you want to say, hey, it's 1 meter, you specify it here. You write down on your paper, unit length is 1 meter, then in the calculation, follow this 1. I'm fine with it. Or if you don't write this, you can say Q divided by, you're calculating Q divided by L equals to something without showing any 1 in the right-hand side. It's fine with me too. But don't just say Q equals to something that without showing L there. You see what I mean? Okay, so that means the equation is wrong. It's supposed to have the area in there. You didn't have include the length, so it's not in the real area. Okay, either you specify 1 meter here to me, or you calculating Q over L. Both of these ways are fine with me. Okay, but just don't say Q equals to something, but without showing the length in the equation. Okay. So before I continue, let me ask you. Now you see this 3 resistance here. In the entire system, you have 3 resistance. Which one is the dominant resistance? The control resistance. The smallest or the largest? Well, if there's no resistance, as if the heat transfer, the resistance is not there. It's just like passing 100% of the heat. So then you have no control, right? If you have a larger resistance, that means actually it affects the heat transfer significantly because of this material. Is that right? So if you want to use the overall heat transfer coefficient idea in the textbook, U, if you want to use UA, this idea, okay? Okay, so if you want to use it, you have to identify which one is the significant, most dominant controlled material, okay? Control the resistance. In this case, the outside convection, HO, exterior convection has a much, much greater resistance than the other two. So this is the characteristic heat transfer material, okay? Controlled material. So the area, basically the question is which area you're gonna use when you convert into U, right? So this is the area, A out will be used. Because your U equals to what? Your U, basically UA equals to 1 over UA equals to 1 over us, right? That's what we wrote before, right? So in other words, U basically equals 1 over delta A times delta R. Okay, but don't worry about this. I just don't want to confuse you. Just use this. Let me erase it. UA. So when you're calculating UA, you need a area. Erase. Let me erase. Just erase this whole thing. Okay, so after you calculating all the R's, okay, 1, 2, 3, okay, then your UA adding them together. So oh, okay, he asked me to calculating the U, so I need to do that. Okay. So you need to separate the A. Okay, that makes sense. So U equals to 1 over A 0 summation of R. Okay, because U is overall heat transfer coefficient. So you need to add the delta R together times a characteristic area, which is, in this case is the most dominant heat transfer mechanism is R0. So A0 is the area, okay? So based on this calculation, your U is 7.55. No, 7.577 watt per meter squared C. Okay, notice the unit is the same as H, right? We use a similar approach, similar form. So based on that, this is the U. This is what the question, calculate the overall heat transfer coefficient. Okay, this is the process. Okay, after you're getting all the R's, okay, so 1 over the characteristic area times the summation of all the R's. Okay, that's your U. So then your Q will be equals to U times A times delta T. Okay, so it will be 7.577 times that big area, pi times 0.0266 times 1, then times, what is the delta T in this case? 30 degrees. Okay. Equals about 19 watt. Okay. So, but if you want to use, hey, if you want to, I'm out of paper here. If you want to use, just directly use the thermal resistance, which I prefer, okay? Although I'm trying to teach you the both ways. But if we directly already calculate R over R, okay? How about you just use delta T over the summation of the R's? Is that the Q? Okay, it will be slightly different as 19. Hey, you have a calculator, can you do it? Let's say 30 divided by the summation of these 3 R's. It will be probably 18.99, something like that. Okay, it's close enough. Okay, both ways should be close enough because in this case there is
I got 19.
Oh, you have what?
I got 19.
Oh, you got 19. Okay, so it's totally close. You see, in this case, doesn't matter because the difference is tiny, very tiny because the area. Okay, we choose the R0 because R0 indeed is the most dominant resistance. Look at the value, 1.575. It's like 1,000 times more than the conduction. Okay, it's like 300 times, no, 500, yeah, 1,000 times, more than 1,000 times, 10,000 times comparing to the conduction, 1,000 times comparing to 500 times at least comparing to the inner convection. So this is the dominant. So you use that area, it's okay because basically what it says is it's only the outside convection is, is dominant, and then the other two doesn't matter, basically what it says. That's why when you use the U A delta T, you just choose that A, doesn't show much difference. But if you have a case, the three R's are similar, and then the area has significantly different, very big tubes, very thick layer. The area are very different, but the R's are about the same level. Okay, then you can use this. Then if you use this, then you will see, first of all, which one is the most dominant heat transfer material? Which one is the most dominant resistance? You don't know, it's about the same. So which A you pick, right? So in that sense, to me, it only works for situation like that in this example, okay? One is very, very dominant comparing to the others, okay? Then UA delta T is, I think it's good, it's okay, okay? Be careful, okay? In a lot of textbook or in real-time application, people indeed use U, okay? Seems like people like the idea of UA delta T, just like HA delta T, okay? Heat transfer coefficient, okay? This is the, seems like the good conceptual idea, okay? But when you're actually doing it, be careful. You could get different value of the heat transfer rate by using UA delta T, comparing to delta T over thermal resistance. I think delta T over thermal resistance is totally correct, whatever situation. Okay, that makes sense? Okay, any questions? But I really want you to know both, okay? Because in reality, in practical application, people use UA delta T, okay? A lot, you can see. Okay. Also, if the area for every layer have the same area, then it doesn't matter, it's correct. It's the same as so delta T over resistance, same. The two approaches are exactly same. Only when the areas are slightly different or the area are very different between each layers, then that's a concern. Be careful, okay? That would be a concern, but sometimes it's still okay, okay? You as an engineer, you need to justify it, okay? Is that good? Any question so far? Now, I just really want you to fully memorize the two different methods, okay? At least delta T over R is really simple to memorize, right? Delta T over summation of R, depend on the series or parallel configuration. That summation R could be different, right? We presented that. So, but that's really simple. Just remember this. Then you can totally forget whatever you learned in chapter 1. Okay. Ka delta T over delta X, dt over dx, or HA delta T. Then it will be included in this simple equation, delta T over summation of R. That's your heat transfer rate. Okay, that's the beauty of it. And also this way, this is the secondary, okay? Overall heat transfer coefficient, UA delta T. But remember, keep in mind, U is also calculated from the R's. So it's not much different. Okay, that's a good stuff from this chapter, okay? I have 15 minutes, less than 15 minutes. Let's talk about another thing here, interesting. Another thing is kind of interesting to you, maybe against your intuition. Okay, so, okay, let's create another. It's called critical thickness of insulation. It's very practical. Okay, during installations, people will always ask a question: how thick my insulation need to be? Okay, how thick my insulation need to be? Well, thicker is better, but the thicker, the more expensive, right? You know it, right? So sometimes you keep it into, economics is all about engineering. Engineering basically, it's all about economics. And when you work in industry, you will know everything is money. So how thick? What the thickness should be? What is the critical? That's the critical thickness. Actually, the thing is, you probably don't believe it if I say this. If you put an insulation on something, it might increase the heat transfer. Oh, that's totally against my intuition. When I first time I heard this, what the heck you say? You put the insulation on it, it will increase heat transfer?
Like it depends on the material?
Well, whatever material, you put an insulation. If you don't think about the thickness, there will be a situation, whatever material you put on as the insulation, it could be increased heat transfer. Okay, let me tell you why. Okay, if you draw something like this, you see. Okay, so basically, let's say this is the insulation. Let's not use cylindrical on it. Let's just use a wall. How about that? Okay. Let's say, hey, let's have a wall. Okay. I put in insulation on it. This is the insulation material. This is just the wall and whatever you want to keep insulated. Okay, so think about this. You have two situations here. This is the same wall without the insulation. You have heat transfer going on, right? Okay. I think still probably, sorry. I think the better way is still using the cylinder because now the area is the same. I don't see the difference in the area. Okay, let's come back. Come back to that cylinder problem. Okay, that probably is more clear. Okay, you have a pipe. Okay. Oh. That's more clear. Okay, so a pipe that without insulation. So which one has a greater heat transfer? Well, you will say, hey, you lose heat, temperature, because of the thickness, right? Thickness. But notice now the convection heat transfer here. Okay, let's say delta T is the same, Ti, T infinite.
Dr. Zhang, you froze.
What? I froze?
So you keep cutting in and out.
Oh, okay. I'm sorry. So can you see me now? Okay, okay. Let me say it slowly. How about that? Say slowly always helps. Okay. Let's say you have the inside temperature and the outside temperature. Okay, okay. Two situations, right? Look at this. H is the same. Delta T the same, right? Okay, how about the area? Which case has a bigger area?
The top one has a bigger area.
Okay, the top has a big area. So if this installation is totally terrible, is nothing, you know, have 0K, then the uppercase actually has a bigger, more heat transfer than the lowercase. Okay. Oh, but the good thing is, hey, because we have insulation here, this have a K. So our total is delta T over RH plus the K in there, right? This is the RH. Although RH actually is bad because of the, here also has just delta T over RH. Okay, although this RH is actually bad, 1 over HA, the area is bigger. Okay, but you have an additional RK there. Okay, which will help. Okay, did you see the process? Okay, but what if the RK is smaller than the difference between these two RHs? Well, it helps a little bit for the insulation, but it doesn't help enough to overcome the area increase. Okay, okay, indeed, it could happen. Okay, if your insulation is too thin, if your K is too little, okay, it could, then actually, because the area increased, then you have a bigger heat transfer from the convection. And your insulation is not enough to overset the difference in the increase the convection. Then you actually, even with the insulation actually increase the heat transfer. It actually is totally opposite of the process. Okay, so keep in mind, when you put the insulation, always put thick enough. So what is the critical thickness? Okay, now I tell you this, I put this graph. How many time I have? Okay, I have 7 minutes. This is the thickness. This is the heat transfer thickness of the insulation, okay? Actually, heat transfer increases, then start to decrease. Okay. It's actually, heat transfer is like this. If your thickness is too little here, if within this range, if it's too little, then the heat transfer actually increases. It's pretty bad. Okay. Then if your thickness is thick enough, then the heat transfer, of course, going down because this is called insulation, right? It help you reduce the heat transfer. Okay. Okay. So that's a critical. So this is actually the equation 2.17. The 2.17, if you draw a curve, it will be just like this curve that represented the equation 2.17. Okay. So when R increases, when R0 at the beginning increases a little bit at the beginning, then the thickness related to the R0, right? So if you reform the equation 2.7, make it in terms of the difference between the two layers, become a thickness, then it will look like this. So if you take the derivative respect to R for equation 2.7, remember in calculus, you take a derivative for that function. If it's equal to 0, that means that's a maximum or minimum point. You remember that? So in order to find if there's a maximum or minimum point, you just take a derivative for a function. And if it's possible to be 0, that means that exists a maximum or minimum point. Okay, I don't know if you remember this, but that's what I learned in calculus. We talk about that. So basically, take a derivative for equation 2.17. Actually, it's possible to be 0. That means indeed there has a maximum point exists. So that is the critical thickness. Okay. By doing that, you can calculate the critical thickness. actually representing this point equals K over H. If the thickness equals to K over H, you will see a peak, okay, in the heat transfer. Okay, this is called critical. Critical thickness. Okay. So smaller, that critical thickness actually, if you find a calculation, you will see it's pretty tiny. Okay. You usually depend on the K and the H for your situation. You compete, basically competing conduction and the convection, right? See which one has more. Convection is bad, you lose heat. Conduction is try to stop you from losing that much heat, okay? So based on this value, usually it's pretty tiny, okay? So, but do a calculation when you try to design some insulation, because that matters, okay? So you wanna have the lowest, thinner insulation because you're gonna save some money, all right? You wanna thick enough to make sure you have enough insulation to the process, okay? So you need to check that. Make sure your thickness is greater, much greater than this critical thickness. Then you should be safe, okay? You should have a good performance on the insulation, okay? Okay, I think that's good. That's it for today. I covered section 2.6. Okay, next time we will talk about the heat source. So far, we never talk about anything heat source. Everything we don't generate heat. Well, we'll probably have one or two example or homework problem talk about heat source. But mostly we talk about heat transfer without the heat source in the material. Okay, next time we will talk about 2.7, 2.8. It's about the heat source in the material, then what is the conduction heat transfer? Okay, so I guess that's it for today. Any questions before we leave?
On Friday, can we go over stuff about the project?
Oh, project. What's your question? I thought I posted the project description on Moodle. Is it not clear enough to you?
No, it is. Just if we have questions, can we ask them on Friday?
Oh, sure. You can ask anytime. You can even text me, ask any question about the project. The due is next Monday. So you still have one week to go. Okay. The first project, I don't expect to see a very complicated project. It's okay. Okay. Something, try to measure something, then substitute the data you measure into the equation. If the equation works, that's good. That's the goal. Okay. To verify the theory, verify the equation. That's what I mean. Okay. Okay, good. So see you Friday.
Professor, are you gonna take the quiz on fluid mechanics today?
I don't know. I'm not pre-announced any quiz. Quiz is surprise quiz. All the quiz will be surprise quiz. Yeah.
I did have a question for you. You lost me before. I think it was my cell reception. When you got the 0.0226, I know you said you were multiplying something to get that, but what did we multiply and then add to get that?
Oh, because the thickness has two layers. We're calculating diameter. It tells you the thickness of the ring is, as a material is 0.8 millimeter, something like that, right? But yeah, when we calculate the diameter, you add both sides.
Okay, yes, sir. Thank you so much.
You're welcome. You're welcome.
Professor,
yes.
They are distributing some hard sport in the college, so I got to stay in the line. So if I miss the quiz, that's why I was wondering that if I have to extend the line for like
everybody,
2-3.
I think I will announce it in the class today. Everybody can miss one or two quizzes. That's fine.
Okay.
Okay.